Okay, so picking up where we left off in the previous video, let me get rid of these. So we have, for example 5, I want you guys to pause the video and try. We're not graphing anything, you just tell me what transformations took place to get f of x to g of x. So hopefully you had a chance to give that a try. Here's my original function, which is going to be a growth because b is bigger than 1. And then this 3, if you recall, has stretched it vertically by a factor of 3. And then since this -1 is on the inside with the x's, not on the outside with the y's, that, remember, is a shift 1 unit to the right because it's x minus 1. That's all we had to do. What transformations take place for that function? For the graph, you can put it in your TI and see that it's going to be a growth. Example 6 says, give the equation of the exponential function given. We got 2 parts. So they give us a point on the graph, and they want us to give the exponential function. Well, we know an exponential function has f of x or y equals c b to the x as its regular form. And we also know that this guy is going through 0, 1 from what I see in the picture, which means c must be 1 in this case. Notice if I plug that point in and do all the work, I will have 1 for the output and 0 for the input for the x, and b to the 0 is 1, so c will be equal to 1. So I can use c equals 1 by actually using that ordered pair for my input and output, or just visually see that the c is always the y-intercept, so that's got to be 1. Now I'm going to use the other ordered pair. That's my x, that's my y. So 1/5 is going to be equal to b to the -1 for me to be able to find b. Well, I'm going to use reciprocals. That's 1 over b. Then I'm going to cross multiply those guys, and b must be equal to 5. So my final function is y equals 1, I guess, for my initial amount, 5 to the x, or just f of x equals 5 to the x must be the graph of that red function they're giving me. You guys try part B on your own by pausing the video and coming back. So again, it said an exponential function, so I'm going to start with the basic format. And again, they're labeling for me that it goes through 0, 1. So I know c is going to be 1. If that was going through 5 or something, I would make the c be equal to 5. Then they're giving me this ordered pair. So I have my x and my y. My y is 8 and my x is -3. So basically I have 8 equals 1 over b cubed that I'm dealing with. If I think of that as 8 over 1 and do a cross multiplying, I'm going to get 8b cubed equals 1. In other words, b cubed equals 1/8. And we can get to our b value being 1 over 2. Not a y, but a b value. So my b must be 1 over 2, which means my function is y equals 1 was the initial amount, a half to the x. And that makes sense because the graph clearly shows a decay. As I'm going to the right, I'm going down, versus the previous one, as I was going to the right, I was going up. So things make sense for that one. Let's go look at example 7, which is an application problem. It says a certain breed of mouse was introduced onto a small island with an initial population of 320 mice. So we know the initial amount, which is our c value. And scientists estimate that the mouse population is doubling every year. So it's doing that thing where as we move to the right, you keep multiplying by 2. Find a function n that models the number of mice after t years. All right, well, we got y equals c b to the x, or f of x equals c b to the x. They already told us the initial number of mice, that's 320. And they're doubling. That means if they're doubling every year, their growth factor is 2 because they keep multiplying by 2 each time. So my base is 2, and the input is t in years, so I'm going to put t, and the output is n, which is the number of mice. I'll put n of t on the left. So that's the model. N of t equals 320 to start with, and then they keep doubling every year. If it said they keep tripling every year, the base would be 3. Estimate the mouse population after 8 years. Well, that's easy. I just have to go and plug in 8 for my t. So we got 2 to the 8, which is 256, times the 320 we started with. So it looks like we end up with 80,920 mice after the 8 years. The population keeps doubling every year. Okay, let's keep some of the things we learned in mind and connect it to percentages that could also relay exponential growth or decay. Quantities that grow by a factor, which is what we talked about, that factor b, are exponential in form, and they have cb to the x as the equation. Quantities that grow by a percentage are also exponential in form, and that equation is very similar to the previous one, with the b value being replaced by how much it's growing by as a percentage, being 1 plus r if it's growing by a percentage r, and 1 minus r if it's going down by a percentage r. So r is known as the growth or decay rate, and if b is less than 1, remember, we're losing a percentage, and we have a decay, and we would be doing 1 minus r because you're losing a percentage. And if b is bigger than 1 in our cb to the x, we're gaining a percentage, and we'll have growth for that problem, and we would be adding that percentage to get our b. So basically, a percentage gets added to your initial amount by either going up or going down. So we're basically going to tie in these two guys with the examples we look at. Number 8 says, let's say you have 3 people infected with the coronavirus. So we're going back to that, similar to what we did at the beginning of the video, in the previous video, part 1 of this video, and in the state you live in. But the number of people over the next weeks is growing by 50%. So they give you a percentage. When there's a percentage increase, that's also going to behave exponential in form. Give a model that represents the number of people p after t weeks, and how many people will there be after 1 month. So basically, since there's a percentage, we'll start with a 1 plus, and since it's growing, I'm going to add the percentage, 1 plus r to the t. And that means, well, I started with 3 people. That's my initial amount. Oh, this I should call c, you guys. So that should be c to keep it consistent. So my initial amount is c. And since I'm going up by 50%, that's 0.50 in decimal form. So percentages, you always put them in decimal form when you use them to do math with them, raised to the t, which means I have p of t ultimately equals 3 times 1.5 raised to the t as my equation. So I'm going up by 50% for every unit of time. And after 1 month, when 1 month is equivalent to 4 weeks, and since this problem t was in weeks, we're going to do p of 4 weeks, which is a month, 3 times 1.5 raised to the 4, and get 15.1875. So we'll say something like 15 people after 1 week, after 1 month or a month were infected with the virus. Now keep in mind, this was a 50% increase every week versus, let's scroll back up to the very beginning of this section when we talked about people doubling. Notice at the very beginning when people were doubling, when we saw this model where 3 was the initial amount and the base was a 2 instead of 1.5, by the time we were in the 4th week or in that month, we had many more people infected. We had 48 people infected versus if there's only a 50% increase like we're looking at now, at 50% increase versus doubling, we end up with, let's scroll down, 15 people being infected. So remember, a 50% increase versus a base of 2 versus for the other one where I had 2 to the t. A base of 2 basically means you have 1 plus 1 to the t, so you have 100% increase for every unit of time. And that's a quicker growth versus the 50% increase. So this piece tells me the increase, 50%. And if I write the base 2 as 1 plus 1, that's really 100% increase, which makes sense. When something is doubling, it's replicating itself, there's going to be 100% increase. So the bigger the base, the quicker. Let's go look at the same problem with the toilet paper issue, where we had 1,000 rolls to begin with at target, and every second, in this case, it's being reduced by 25%. Give a model that represents the number of rolls after X seconds. So we've got y is equal to cb to the x, but in this case, since they're giving me a percentage, I'm going to use 1 plus r or 1 minus r. I started with 1,000 rolls, and since I'm reducing 25%, I'm going to do 1 minus 25% to the x. So my function is basically 1,000.75 to the x, and they want me to use n for the number of toilet papers, so I'll use n of x is 1,000.75 to the x. And again, comparable to the previous example there, I was gaining 50%, so I added that to 1 to get the base. Here I'm losing 25%, so I subtracted that from 1 to get the base b. And how many rolls will there be after 3 seconds? Well, that's just n of 3, which is going to give me about, I guess, 422 rolls, let's say, after 3 seconds. Versus, let's go look at the beginning when we had the case where people were, I think, grabbing the rolls much quicker. What happened in that case at 3 seconds? So here we have 422 rolls with 25% reduction every unit of time, meaning my base is 0.75. Versus, remember this problem where the base was actually a 0.5. So that was a bigger loss per unit of time. If I have a 0.5, by the time I get to the 3rd second, I only have 125 rolls left. Because I'm decaying much quicker, I'm losing 50% every second versus only losing 25% in the problem that we just looked at. So a 50% loss starting with 1,000 versus, I guess, a 25% loss, which is what we did down here, left me with 422 rolls after 3 seconds versus the 125 for a quicker decay there. Last thing we're going to look at is a compound interest formula, but let's do that in another video, and that'll be our last video for this section.